So in the previous semester, we have been to the calculus part. Now, in this semester, we'll go with the numerical analysis part. Okay. So numerical analysis for numerical methods plays a very important role. Okay. So when we think of the mathematical model of the process, okay, or mathematical model of some plant, then we try to understand the features of the plant, features of the process numerically. Okay, and that's why we try to get everything in terms of numbers. Okay, and hence we need to understand the numerical method. So there are several equations we come across, and then we need to understand what type of equation is that. And once we understand what type of equation is that, we need to know the method which will be applicable for that. Okay, so that we have to understand. So here, first of all, we'll start with some basics. Okay, so we'll start with the transcendental equation. Okay, I hope you are able to see this, right?
Yes, sir.
Yes, sir.
Okay. So first, we need to understand the transcendental equation. So what is meant by transcendental equation? So basically, we know about the polynomials. Okay, but there are.
Sir, can you please speak a bit loudly?
Yeah. Okay. So there are the functions other than the polynomial. Okay. Now, those functions, for example, we have sine, cosine, trigonometric functions. We have logarithmic functions. We have exponential function. Okay. So these functions, so if any of the equation includes or contains these functions in that equation or that expression, we call transcendental. Okay. Now, once we have the transcendental equation, okay, then what are the methods that can be applied? Okay. So first of all, we'll try to understand the Newton's method. This is also called as Newton-Raphson method. Okay. So we go with numerical solution of transcendental equation.
Sir, can you please repeat what's transcendental equation?
Yes, surely. Okay. So most of the times we are familiar with the polynomials, right? Okay. But there are more functions than the polynomial also. Okay. So for example, we have sine, cosine, or in general trigonometric functions. We have logarithmic function. We have exponential functions. Okay, so the equation which contains these expressions or functions, we call them as transcendental equation. Is that okay?
Yes, sir. Got
Sir,
it.
can you please repeat that previous statement?
Okay. So in simple words, transcendental equation contains logarithmic function, exponential function, or trigonometric function. So if you find any one of this, okay, then we call them as a transcendental equation. Okay. So first method that we are going to study to solve this transcendental equation is Newton's method, or this is also called as Newton-Raphson method. Okay. So when we are able to get the root or the solution of this transcendental equation, so basically we are looking for the solution. Okay, so we have our equation. Okay, so this is going to be x-axis, y-axis, and origin. Okay, suppose we have a function. This is f of x. Now we have the interval a to b. So this is the interval a to b. So what this point is? This point is a, f of a. And what this point is? This point is b, f of b. Okay. Now our target is to find this x. So our target is to find this x such that f will be 0. Okay. So what we can say is, we can say let f of x is equal to 0 be the given equation. Okay. Then point x0 is root or solution if f of x0 is equal to 0. So we have to find the value of x such that this function will be 0. So you can see here it is the x which lies in between the a and b such that f of x is going to be 0. Okay, so this is our target point. This is the solution that we want to find. Okay, now how we are able to find, or what is the Newton-Raphson method says. Okay, so you can see from the curve. Okay, what we have assumed? We have assumed that f of a. Okay, so we have assumed that f of a is less than 0 and f of b is greater than 0. So when we have f of a is less than 0 and f of b greater than 0, then by the theorem, when the function is going to be continuous and it has a maximum value and it has a minimum value, then it attains every value in between its maximum and minimum. Okay, so this is the theorem. Now, here for this function, the minimum value is f of a, the maximum value is f of b. So f of a is less than 0, f of b is greater than 0, and that's why the theorem guarantees that we have a root in the interval a to b. Okay, so we have a root in the interval a to b. So now, how we are able to get this root? Okay, so we have, these are the assumptions that we need to understand. So let f of x, so being a transcendental equation, it is continuous and differentiable moreover. See, polynomial is continuous and differentiable. Trigonometric function is continuous and differentiable. Logarithmic function is continuous and differentiable. Exponential function is continuous and differentiable. And the transcendental equation is exactly the linear combination of all these terms. So that's why it is going to be continuous and differentiable. So if I say differentiable, that is sufficient to say that it is continuous. Is that okay?
Yes, sir.
Yes, sir.
Okay, if I say the function is differentiable, that means it is going to be continuous. So B, the differentiable function defined the interval A to B. Okay, so it is defined in the interval A to B and it is differentiable. Okay, so what the point we can consider to start this method? Okay, so you can see this graph. Okay, so A is here and B is here, and this is the target. This is our target, that we have to get this value of x such that f of x is going to be 0. Okay, so what do you think? Which is closer, A or closer or B or closer?
A.
A
A.
is closer. Okay, so very good. Now here you have a graph, so you can easily see that A is closer. Suppose you don't have a graph, then how you will decide that A is closer or B is closer?
F of x
We can
minus
find the
f of
distance.
Yes, so we can choose the value of f of x, and then from that we can decide. But the better way to get a closer point than A and B is the average of A and B. So average of A and B will be here somewhere, right? It will be
Yes,
here
sir.
somewhere.
Yes, sir.
So that will be a better one to say that the A, then A and B, this point is going to be more closer. Okay, so what this point is? This point is A plus B by 2. Okay, average of A and B. And that's why we consider, since f of A is less than 0 and f of B is greater than 0. And we consider the initial point or solution as x0 is equal to A plus B by 2. Okay, what we consider? X0 is equal to A plus B by 2. So this will be our initial approximation. So this is going to be x0. Now, once we know x0, how we are going to calculate the next x1? Okay, so we can say by Newton-Raphson method. We have the general formula xn plus 1 is equal to xn minus f of xn on f dash of xn, where n is running from 0, 1, 2. Okay, so this is the formula for the root of the transcendental equation by the Newton-Raphson method. Okay, so here we have seen that f is going to be differentiable, so we don't have any problem with this f dash at xn. It is going to be non-zero. We assume that this is going to be non-zero, because if it goes 0, that means xn is going to be the root exactly. Okay, so we have xn is going to be approximate root, and that's why this term will not be 0 or will never be 0. Okay. Now, is
Sir.
there any doubt up to it?
Yes, sir.
Yes, please.
Sir, how did you prove that x naught, that is a plus b by 2, will be a root of the equation? I did not understand that part.
No, it is
Why
not the
will-
root. It is initial point there we want to start. It is initial point where we will start our method.
Okay, sir.
Excuse me, sir.
Yes, please.
Sir, if suppose the initial point itself is the actual solution, then this
Yes.
denominator will become 0. So this formula won't be applicable, right?
So we got the actual root, no?
Yes, sir. So we won't need to use
We
the
won't
formula.
need this formula then. If
Yes,
we
sir.
know, if we know actual rate, then we don't need this formula.
Yes, sir.
This formula is applicable as we don't know the value. Okay. To find that value, we need this formula. If we know that it is going to be the root, then it's done. Our claim is achieved. Our problem is solved. So is that okay? You're done?
Yes, sir.
That's good.
Yes,
Any
sir.
other query? Is there any other query?
No, sir.
Okay, good. Okay, so here n is running from 0 onwards. Okay, so if I put n is equal to 0, then I have to use x0 and then calculate x1. If I know
Sir.
x1, yes,
Sir, sorry to interrupt, but can you please just tell that why did we take a plus b by 2 as our initial point? Is
oh
that
yes, yes. Okay, so here as we saw this graph, okay, so you can see this graph.
yes, sir.
Yes. Okay. So from the graph, okay, now we want a root or initial point closer to the root. Okay, so here A is the point, B is the point, and X is our actual root. Okay,
Yes, sir.
so we want to start this method, and to start this method, we need one approximate root closer to this actual root. Okay,
Yes, sir.
so now you have to compare this A. We don't know X, okay, because that is our destination where we want to go. And this B. So the information available with us is we have f of A less than 0, we have f of B greater than 0. And this guarantees this is going to be a continuous differentiable function. So it guarantees that it will attain every value from f of A to f of B. And 0 is included in this interval. So we want to move closer to the value of x such that f of x becomes 0. That is our target. Now we have A and B. So how you can guarantee which is closer to the root? A is closer to the root or B is closer to the root? Because here we can see the graph, so we can say that A is closer. Okay, but when I do not have the graph and I want to guarantee something that it is closer to the root. Okay, so I can say that the root is closer to A plus B by 2. Okay, because it is exactly the midpoint of the interval. Okay,
Okay,
so
sir.
here to start, we are using midpoint of the interval. Okay,
Okay, sir.
okay, that's great. So is there any other query? So if you don't have any query, then we can think of the example based on this. Okay, so let us try to understand this with the help of the example. Okay, so we'll go with the example. Okay, so I hope you are able to see this. Are you able to see this?
Yes, sir.
Okay, so using Newton-Raphson method, this has to be Raphson. We will write the question using Newton-Raphson method. Find the root of x cube minus 2x minus 5. X cube minus 2x minus 5 0. Correct? Up to 4 places of decimal. 4 decimal places. So remember this, our accuracy is at least 10 raised to minus 4. Okay, that is the accuracy you need to work with. Okay, so we go with the solution. What we have, like f of x is equal to x cube minus 2x minus 5 is equal to 0. Okay, so we have to find a and b. There is no a and b given, and there is no starting point given. So we have to find this. Okay, so that's why B define, okay, in, okay, so real numbers. Then what we have, consider, okay, so if I put 0, x is equal to 0, what I am able to get? Is it minus 5?
Yes.
Yes. Yes. So this is less than 0. Now, suppose f of 1. So what will have? 1 minus 2 minus 5. That is 1 minus 7. So it is going to be minus 6, which is again less than 0. What happens to f of 2? Will it be 2 cube minus 2 into 2 minus 5, and that is equal to 8 minus 4 minus 5. So is it minus 1 again less than 0?
Yes.
Yes. Okay. Now f of 3. So what will have? 3 cube minus 2 into 3 minus 5. So what we get is 27 minus 6 minus 5. That's going to be, we have,
16.
yes. Is it less than 0 or greater than 0?
Greater than 0.
Definitely greater than 0. So here we got one value of f of 2, which is less than 0, and the other value of f at 3, which is greater than 0. Okay. So what this means, your function is negative at 2 and the function is positive at 3. So we can say, hence, the root is in the interval 2 to 3. Okay, so the root is in the interval 2 to 3. That means there exists a point in this interval 2 to 3 such that f will be 0 at that point. Okay,
But we are taking these points randomly.
yes,
We are taking the 0, 1, 2, 3 randomly.
yes, we are taking 0, 1, 2, 3 randomly. Okay, but usually we go in that way only. We try to find out the root in positive one. Okay, so that's why one by one we are trying. Okay, we are trying to see that what is the trend given by this function. Got it?
Yes, sir.
Okay.
Excuse me, sir.
Yes, please.
Sir, but for here, f of 0 and f of 1 are also negative. So what we have
Yes.
to take
Yes, exactly.
interval?
Yes, exactly. Okay. So if I take 0, still it is negative. Okay. If I take 1, still it is negative. Okay. So we can try to understand this. Okay. So this curve is like this. Okay. If I take here at 0, it is negative. 0, 1, 2, and 3. Okay. So at 0, it is going to be negative. At 1, it is going to be negative. At 2, it is going to be negative. And at 3, it is going to be positive. Right?
Yes.
Are you
Sir.
getting this?
Yes.
Yes.
Sir.
Okay. So
So
if it
in
is
this
negative
question,
here,
the equation isn't.
negative here,
Excuse me, sir.
and this is negative here. Yes.
So this equation isn't transcendental. So then,
Yeah,
how
it is
can
not
we?
transcendental. It is just a polynomial.
So we can still apply the method.
Yes, we can still apply the method. Okay.
Okay, sir.
Yes. So first we'll try to understand the simple polynomial, then we'll go for transcendental also. Okay.
So sir, all the methods.
Yes.
Sir, I was asking all the methods for solving the transcendental equations will be valid for polynomials.
Yes, obviously. So if you can solve the transcendental equation, then you can solve the polynomial, definitely. Okay. Yeah. So here we got these 3 negatives. Okay. And we got 1 positive. So here we have positive. Correct. So now why not this 0 and 1? Why we have chosen 2? So this is our actual root x. And we have to move closer to x. So tell me whether 0 is closer or 1 is closer to x than 2. Which one is closer?
2.
2 is closest.
So that's why we have chosen the interval from 2 to 3. What idea?
Yes, sir. Thank you, sir.
Okay, yes. Okay, so we got here the interval. Okay, and in this interval, we got the root is in between 2 and 3. Okay, and hence what we do is consider the initial approximation as x0 is equal to 2 plus 3 by 2. So is it 2.5?
Yes.
Yes.
So we got x0 is equal to 2.5. Okay, this is the initial approximation that we have. Okay, now we need to understand the function. So we have f of x is equal to x cube minus 2x minus 5. And hence what we have f dash of x. Okay, so what will be f dash of x? Is it 3x square minus 2?
Yes, sir.
Okay, so we can write here by Newton-Raphson method. We have, okay, so what we have? We know xn plus 1. Okay, xn plus 1 is equal to xn minus f of xn on f dash of xn. So we can write this as xn minus f of xn. So it is going to be xn cube minus 2xn and minus 5. This term divided by 3xn square minus 2. Simplify this. So we can have xn into 3xn minus 2 minus of xn cube minus 2xn minus 5.
It will be 3xn square minus 2, right? In the first term.
Yes. Okay, so we got here 3xn square minus 2. Okay. So that's what we have. Got it. Now simplify this. So we can have this is equal to 3xn cube minus 2xn minus xn cube minus minus 2xn and minus minus plus 5. And here we got 3xn square minus 2. Is that okay?
Yes.
We got xn plus 1 is equal to, so it will be 2xn cube plus 5 upon 3xn square minus 2. You're getting this term?
Yes.
Okay.
Yes, sir.
When n is going to be 0, 1, 2, 3 onwards. Okay, so now this is the general formula to find the root for this particular example. Okay, this is the general formula for every example. So for every example, we have to find this expression. For this example, we got xn plus 1 is equal to 2xn cube plus 5 upon 3xn square minus 2. So is that okay up to here?
Yes, sir.
Okay.
Yes.
That's good. Now we have what we have x0 equal to 2.5. We have calculated this x0, no? So here it is. We have calculated x0 is going to be 2.5, right?
Yes, sir.
Okay.
Yes.
So now we have to put this value, okay, in this expression. So we can get x1 is equal to 2 into 2.5 bracket cube plus 5 by 3 into 2.5 bracket square minus 2. Okay, so this is what we get the value as the first approximation. This is the initial approximation that we have got. Now tell me what is the first approximation. Can you tell me the first approximation? What is value?
2.1641.
Okay. What about others?
Same, sir. Same, sir.
Same, sir.
Sure.
Same, sir.
Okay.
Same, sir.
That's great if you are getting the same one. Okay. So now what you have to do is you write this in fraction and you have to write the expression what we have as a function. Okay. So 2 into x cube. Okay. It's going to be x cube. We have plus 5 and the denominator we have 3 x square. Okay, and it's going to be minus 2. You can calculate. So when you last calculate, you have to input the value 2.5, and so you will get the root. So what is the first approximation to the root? It is going to be 2.1641. See, we have to find out up to the correct 4 decimal points. So we'll write some more. So we'll write 79 also. Are you getting this? Is that okay?
Yes, sir.
Yes,
So this is the
It will be
first.
2 point.
2.16, sir.
Yep, sorry. Okay, so it is going to be 2 point. So this is 2 point, right? So now, what we got? We got the first approximation. Okay, so let us try to have the next approximation. So now what we have to do is, we have to put this value of x1 in this expression. Okay, so we have x1 is equal to 2.164179, and hence x2 is equal to 2 into 2.164179 cube plus 5 upon 3 into 2.164179 square minus 2. Okay. Now we get the value of x2. Okay. So value, what is the value of x2? You calculate, and I'm calculating with you. Okay. So are you getting this 2.097135? Getting this? Are you able to calculate this?
Yes, sir.
Yes. Okay. That's good. So now, once you get this value, again you have to put this value in this expression. Okay. So whatever the value we are getting in the previous iteration, that we have to use in the next iteration. So let us calculate what is the next iteration. So we got the next iteration as 0.094552. Are you getting this iteration? We have to put this current value in that expression. Okay, or you can give this as equation 1. Okay, you can write here from equation 1 we get. Okay, so right here from equation 1 we got x2. Have you got x3? Writing x3.
Yes, sir.
Okay. What about x4?
So x3 comes as 4,552, sir.
Is 552? Please check whether it is 55 or 555.
Sir, 555.
555.
Okay. So this is going to be 555. So So let's have this 5 and then get the next equation. So what is x4? So is it 2.094551?
Yes, sir.
Okay, that's great. So now you can see that the 4-digit we wanted to match. So we have to go to the accuracy up to 4-digit. So you can see here the digits after decimal point. So in fact, we are mapped or we are matched 5 digits, but accuracy required is 4 digits, and that's why I have asked you to write 2 more digits. Okay, so when you write 2 more digits, then your error will be less and it will be easy for you to understand, okay, how or where we have to stop with the 4-digit accuracy. So here, when the 4 digits after the decimal point match with the previous iteration, then we stop. Okay, so here we got this 4 digits matched, and hence we can say the root of the given equation is x is equal to 2.0945. Okay, so we were asked the answer correct up to 4 digits after the decimal point. That's how we got it here. Okay, so
Yes, sir.
you got this.
Yes, sir.
Yes, sir.
Okay, that's good. So is there any other
Sir.
query? Yes.
Sir, so there will be 3 roots, right? Because it is 3-degree polynomial. 3-degree
Yes,
equation.
surely we'll have 3 roots. Correct. But as I said again, so definitely it is a n-degree polynomial, so we'll have n roots. Okay, but here we are looking for the real root. Okay, so that's why I said this will be in R. Okay, so this is defined in R. We are trying to find the real root. Okay, and the first one that we are getting is going to be 2.09455. Okay, so one root out of that n root we have to find out.
Okay, sir.
Yes.
But using this method, we cannot find all the 3 roots if they are real.
Definitely you can find out. Okay, but then as we got one root lies between 2 and 3. Okay, so you have to go with more. You have to go for 4, 5, 6 and find out the interval first. You need to locate the interval first where the root is. And then once you get the interval, you can find the root in that interval.
Okay, sir.
Okay. Is there any other query? All of you got this example?
Yes, sir.
Is there any other doubt? Is there any doubt?
No, sir.
That's good. Okay, so we are seen one example. Now let us go for the another one. Okay. Let us try to solve the another example. Compute the x log x is given to the base 10 minus 1.2 is equal to 0. Using Newton-Raphson method. Okay, so this is the given example, and then we have to find the root of this equation. It is a real equation, a real root we have to find out, and transcendental equation. So let us try to find out the initial root and then the interval where the root lies. Okay, so we go with the solution. Here you need to notice that the base is given to be 10 for the log. Okay. So let f of x is equal to x log x to the base 10 minus 1.2 is equal to 0. Be defined in R. We want to find out the real root, so it is defined in R. Okay, then what we have to do is consider. Okay, so if I put 0, this is going to be 0. Okay, and hence it is going to be minus 1.2. So we know log of 1 basically was 0. Okay, so we start with 1, 2, and 3. Okay, so what happens to the value when x is going to be 1? So if I consider x is going to be 1, then this will be 0 minus I'll be having 1.2. So is it greater than 0 or less than 0?
Less than
Less than.
Less than 0. Okay. What happens to 2? Okay. So it is 2 into log of 2 to the base 10 minus 1.2. So calculate this value.
0.3010.
It is the value of log 2 only. So it is 2 into 0.3010 minus 1.2. What is the value you have?
minus
It's
0.5979.
Okay, this is going to be minus 0. Okay,
598.
5979.
5979. 5979. Is it greater than 0 or less than 0?
Less than 0.
Again, it is less than 0. So next we have to calculate what is f of 3. Okay, so it will be 3 into log of 3 to the base 10 minus 1.2.
So it's 0.5980. So the previous one.
This value. Okay. Okay. So calculate is going to be 5979. That's okay. 5979, 5980. Here, our concern is that whether it is less than 0 or greater than 0. Okay. So for f of the value of the function, our concern is whether it is less than 0 or greater than 0. So are you getting this value for 3?
Yes, sir.
Okay, so you can see here, this value is
Yes, sir.
less than 0, whereas this value is greater than 0. So root lies between 2 and 3. Okay, and hence we can say the root of equation is in the interval 2, comma 3. Because for 2 it is going to be negative, for 3 it is going to be positive, and hence the root is in between 2 and 3. And now what we'll have here, so we can think of the initial point x0. Okay, x0 is given as, so what is x0? X0 is 2 plus 3 by 2, and that's going to be 2.5. We got x0 is equal to 2.5. That's what we know. Okay. Now think of the function. So we have f of x equal to x log x to the base 10 minus 1.2. Okay, so here what we have to do is we have to calculate what is f dash of x. Okay, so to calculate f dash of x, first we need to understand this function itself. Okay, so whatever we calculate the derivative, we calculate to the base e, to the natural base. So we can write this function as f of x is equal to x into, this is log x by log 10 to the base e and minus 1.2. Okay, so this term is going to be constant. So we can write this as 1 upon log of 10 to the base e into, this is x into log x to the base e, and this is minus 1.2. And now it is easy to have the derivative. So we can have f dash of x. So 1 upon log of 10 to the base e. And here you will have the derivative u into v rule. So it is going to be log of x to the base e, because we are taking the derivative of this x, that's going to be 1. And now x into 1 by x, and the derivative of this term is going to be 0. Okay, so we got here 1 upon log of 10 to the base e, and here you got log of x to the base e plus 1. Okay, so we can simplify this, hence f dash of x is equal to, this is log of x to the base e upon log of 10 to the base e, and this is minus 1 upon log of 10 to the base e. So we can have, this is going to be
It will be
log of x to the base 10. Okay, and minus, we can calculate this value. So this is going to be plus. Okay, we can calculate this value. So calculate ln. Okay, so log of 10 to the base e. So it is natural log. Okay, so it is going to be natural log of 10 to the base e, and then its reciprocal. Okay, so we have to calculate its reciprocal. So reciprocal, this term is going to be 0.434294. Is that okay? Are you getting this term?
yes, sir.
Yes, sir.
Okay, that's good. Okay, so we got here f dash of x is equal to log of x to the base, log of x to the base 10 and plus 0.434294. Okay, so we got here, we have f of x already. We got f dash of x. Okay, so we are able to use the Newton-Raphson method now. Okay, so we have f of x, we have f dash of x, and we know the approximate root also. What we can say here by Newton-Raphson method. We have what we can have. We have the general formula xn plus 1 is equal to xn minus f of xn on f dash of xn when n is running from 0, 1, 2, 3 onwards. Okay. Now, let us see what we have for. So, we have xn plus 1 is equal to xn minus. This is xn log of xn to the base 10 minus 1.2. This is f of xn. And here, what we got? We got log of xn to the base 10 plus 0.434294. Okay, that's what we have calculated. Let us see. Yes, this is going to be log of x to the base 10 and this term. And here we have x log x minus 1.2. Okay. So simplify this. So we can have xn log of xn to the base 10 plus 0.434294 xn minus xn log of xn to the base 10 plus 1.2. This whole term divided by log of xn to the base 10 plus 0.434294. So if you simplify xn plus 1 is equal to, what is the term we are having? This is going to be 0.434294 xn plus 1.2 on log of xn to the base 10 plus 0.4342 when n is going to be 0, 1, 2. So we have x0 is equal to 2.5. Is that okay? Are you getting this? Okay, so now write down this numerator. Okay, so it is going to be 0.434294 times x. Okay, so it will be times x plus 1.2, and in the denominator it will be log of x and plus 0.434294. Okay, so we have to calculate. Then the value of x we have to put as 2.5. So x1 is equal to, if we put 2.5, then we are able to get this term as 0.27. Going to be 2.746505. Okay, so in this expression, you have to put this value of x. So when we put n is equal to 0, that means this will be the first approximation. And here we have to use x0. So are you getting this? Are you getting this first root? First approximation?
Yes, sir.
Yes, sir.
That's good.
Sir.
Now calculate the second one. So this value we have to use now. Okay. So what is the value you are getting? The second approximation 2.74.
2.70649.
Yes, very good. Okay. So this is the second approximation we got. Okay, now we have to use this. Okay, so the third approximation we got as 2.74064, and we got here 646, right? Okay. So you can see even we do not need these approximations. Okay, so here we can see that the 4 digits are matched. Okay, our accuracy required is 10 raised to minus 4. So here we have matched actually in fact 5 digits, but our accuracy required is at least 4. So here it was 7465. Here it was 74064. Here it is 74064. This 6 digit has the difference. Okay, so the accuracy which is required is reached. So we can stop here for this example. Okay, so we can write here, hence the real root of one equation is x is equal to 2.7406. Okay, this is correct up to 4 decimal places, or even if you can write this also. Okay, so better to write more digits than just past. Okay, so we are supposed to write at least 4 digits. Okay, I'm asking to write more so that the reader will understand that you calculated and you know it perfectly. Okay, is there any doubt in this example?
No, sir.
No, sir.
Only thing is that you need to take care of the derivative, because derivative we find only for the natural base. Okay, we do not find the derivative for any other base. Okay, so we find the derivative for the natural base only. And what we know is log of a to the base b is log of a to the natural base on log of b to the natural base. So this way, this decimal base was converted to the natural base, and then we have taken the derivative. Okay, so in case of exponential function or trigonometric function, the derivative is easy, quite easy. Only thing that when the logarithm function is there and the base is not natural base, then we need to understand how to take the derivative. So first we have to convert it to the natural base, and once we convert it to the natural base, then we are able to find the derivative. Okay.
So
Is there yes?
suppose while we are calculating that f1, f2, f3, suppose one of that becomes 0. So that becomes the root. So we can directly write that this is the root and we do not need to do these further calculations.
Actually, if this usually we look for non-zero root only. Okay, so if 0 is the root, okay, then that you can guess easily. Okay,
No, I am
so
saying while we are calculating while we are putting 1, 2 in the function, suppose f of 2 is equals to 0. So 2
correct.
is the root in this case. So we do not need to use that Newton's. We do not need to do this further calculations, right? You can
But,
straight away write that 2 is the answer.
see, the root is, we are not going to check the value of the function. We want the value of the function to be 0. Okay, we want the value of the function to be 0, not x to be 0.
No, I am saying that while we are calculating F0, F1, F2, suppose F2 becomes 0.
Okay.
So here 2 is the root of the function. So we have got the root of the function.
No,
right?
no,
So
we are
do
not making it. See, this is the difference. We are not making x is equal to 0. We are not looking for x is equal to 0. We are looking for the function to be 0. Such x that the function will be 0. Okay, you are
Sir, he
saying
is
that
telling for
x is,
x is equal
yes,
to 2.
x1 is non-zero, x2 is non-zero, and you are saying that suddenly x3 becomes 0, right?
No, I am saying that suppose f of 2 is 0.
F of 2 is equal to 0. Okay.
So while we are doing the calculations, f of 1, f of 2, f of 3, and f of 2 becomes 0. So 2 is the root.
If you say f of 2 is equal to 0, then clearly 2 is the root. We don't need to calculate.
Okay.
Okay. For example, I'll give you the polynomial f of x is equal to 2x minus x square. This is the polynomial. Okay. So here, what you can say is f of x is equal to x. You can have x minus 2 is equal to 0. Okay. So this implies x is equal to 0 or x minus 2 is equal to 0. This implies x is equal to 0 or x is equal to 2. So here, easily you are able to get the roots. No, we don't need numerical method to solve it.
Okay, sir, I got it.
What the idea? So numerical methods are used if you are not able to find the root by our usual methods. Okay. So usually numerical methods come into picture when we are not able to get the value by using our factorization or the usual method. So when it is not easy to guess the root, okay. So here, in this case, it was not easy to get guess the root. Okay, so we got into the numerical method. Here also, this was a cubic polynomial. Okay, so for the cubic polynomial, it is not easy to guess the root. If it is quadratic, we can use the quadratic formula and get the root. Okay, these examples were very easy. Suppose it is the 5th degree polynomial, then it will not be easy to guess the root, and that's why we go for the numerical methods. Okay.
Sir, is Newton's Raphson method also valid for second degree equation like x square 1?
It is valid for all degree. So the degree cannot be a barrier for this. So it is valid for all the types and all the degree. Only thing is that you will get one root at least. So one root is guaranteed. Okay, and if you want to find out the number of roots, then you must have the number of intervals. So in each interval, you can find one root by using this method. Is that okay? Is there any other doubt?
No, sir.
Okay.
No, sir.
So in the last semester, we have used expansion to find or to approximate the value of a square root. Okay, so we can do it by using the Newton-Raphson method also. Okay, so let us go with that example. Okay, I had asked you find the approximate value of 10 using Newton-Raphson method. So in the last semester, we have used Taylor series method. Here we go with the Newton-Raphson method. So how to solve this? We want to find out a square root. That means I want to find a number whose square is 10. Okay, that means what I have to do is I have to find a number whose square is going to be 10. Okay, so let x is equal to root of 10. So I can write this as x square is equal to 10. So I can write this as x square minus 10 is equal to 0. Okay, so x is going to be the root of this 10 that we want to find exactly. Okay, so what we have f of x is equal to x square minus 10, and that is going to be 0. Now, see, root of 10. So root of 10, can you guess where it will lie other than finding the values?
Between 3 and
3
4.
and 4.
Sure, between 3 and 4, because the square of 3 is going to be 9 and the square of 4 is going to be 16. Okay, so we can see that f of 3 is equal to 9 minus 10, and that is going to be minus 1, which is less than 0. And f of 4 is 16 minus 10, so it is 6 greater than 0. So this guarantees that the root is in between 3 and 4. Okay, so once we know the root is in between 3 and 4, so we can say the root, okay, is in 3 comma 4. Okay, so we have the initial approximation as, what will be the initial approximation? X0 is equal to 3 plus 4 by 2, and that is going to be 3.5. So we got X0 is equal to 3.5. Now consider f. So what is f of x? F of x is x square minus 10, and hence we can find f dash of x, that is going to be easy 2x. Is that okay? Are you getting this?
Yes.
So we can say by Newton-Raphson method, we have, so what do we have? Xn plus 1 is equal to xn minus f of xn upon f dash of xn. Okay, that's what we have. So when n is running from 0, 1, 2 onwards. So here xn plus 1 is equal to xn minus, this is xn square minus 10 upon 2xn. So we simplify 2xn square minus xn square minus minus plus 10 by 2xn. So we can say xn plus 1 is equal to, is it xn plus 10 upon 2xn? Is that okay? Yes. So this is xn square, right? Is this expression okay?
Yes, sir.
Okay. Now we have the initial approximation x0 is equal to, we have calculated this is going to be 3.5, and hence we get the first approximation. Okay, so what is the first approximation we have? Okay, this is going to be, write down this expression in your calculator so we can calculate it easily. Okay, so initial approximation is 3.5, and then the first approximation is 3.178571. Are you getting?
Yes.
Are you getting this? All of you are getting this? Next iteration. So we can have this value to be used. So 3.1785 and 71. So now we get 3.1785 1623
2319.
Yes. So now next x3. Okay. So we can go with x3 as 3.1623 and 19. Okay. So we can calculate this value and we get 3.162277. So we can go for x4. Okay, so if we go for x4, what we get here? 3.162277. Okay, and you can see that we get this. Here we wanted to have the 4 digits, but actually all the 6 digits are passed. So we can say the approximate value of 210 is 3.162277. And this we have seen that it is correct up to 10 raised to minus 6. So our accuracy required was 10 raised to minus 4, but we got this up to 10 raised to minus 6. Okay. So is there any doubt?
No, sir.
Okay, all of you got this?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Okay, that's good.